I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and Rstudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the Geostatistical Analyst extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but Rstudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I'm going to be talking about exploratory data analysis, experimental semi-variogram, model semi-variogram, cross-validation, Kriging interpolation, and also at the end we are going to be working with the map edition with Quantum GIS and also reporting results. This is the fourth video of the Geostatistical Analysis course, and today we are going to be talking about the experimental semi-variogram. The two main topics for this video are going to be the Semi-Variogram Cloud and also the omnidirectional semi-variogram. And we are going to leave the directional semi-variogram for video 5. This video is pretty long, about 1 hour, but after watching this video you are going to have a pretty clear idea what is a semi-variogram cloud and also a omnidirectional semi-variogram and what kind of information you can extract for this kind of graphs and what kind of information it represents. Remember that if you missed the previous video, you can hit at the card located at the top right corner of your screen over here. Okay, let's go to work. The first semi-variogram we are going to see today is the Semi-Variogram Cloud. To see that one, just go here, explode data, and select this option, Semi-Variogram's Covariance Cloud. As you can see in this screen, we have a couple of tabs, but we are not going to talk about the covariance. We are going to talk just about the semi-variogram. Remember to select the parameter you want to analyze. In our case, it's going to be the groundwater. And I'm going to change these parameters here, but I'm not going to talk about it yet because I would like to talk later about these parameters. But I want to make sure that here we have 450 meters. That is the total extension of our area. our area is this one. The longest distance is around 450 meters, and I want to have that distance here. In this graph, we have two parameters. At the x-axis, we have the distance, and at the y-axis, we have the semi-variance. If you select one point here, let's go to select this point here. You can see that this point is created with a pair of piezometers. In this case, it's piezometer 11 with piezometer 6. Then the distance we plot at the x-axis is the distance between these 2 points. And that's the distance from 0 to here, to this point here. And the value we are going to plot for the y-axis is the semi-variance. Now let's go to see in a generic graph the Semivariance equation. This is a general graph for the Semivariogram Cloud. It's not related with our data. And here, as we said previously, we have the lag distance designated with the letter H, and here for the y-axis we have the semi-variance designated with the letter gamma. The lag distance H is an independable variable, but the semi-variance gamma is a dependable variable, and it depends on the lag distance H. Here we have the equation to calculate the semi-variance. Let's go to talk about the parameters of this equation. The first term is the semi-variance. We know already that it's designated with the letter gamma, and it's a dependable variable of the lag distance H. We talk about the semi-variogram because we have this 1.5 here. If we remove the 1.5, we are going to talk just about the variogram. The n is the number of pairs. We are going to use the summation when we want to make the average of a specific area, or also when we want to analyze our semi-variogram with a specific azimuth direction. The next term is known as a tail sample or tail observation. In our case, as we are taking the groundwater elevation, it's an observation. But if you are taking for example, the concentration of a parameter, it's going to be a tail sample. We have to be aware that this term has a spatial component because it's a location where we have UTM coordinates, x and y. And the next term is a different location, and it's separated by the first term because of the lag distance. This is a vector, and this vector is h, and this term is known as a head sample or head observation. Now let's go to see this information in a different graph to have a better idea about all this information. Then, in order to create our semi-variogram, we are going to take a pair of piezometers. As you can see here, in this case we are taking the piezometer 20 and the piezometer 54. The piezometer 20 is the tail and the piezometer 54 is the head. And these two piezometers are separated by a distance h. And also we have a specific direction with respect to the north. That's the Azimuth Angle, and here it's approximately 50 degrees. The Azimuth Angle, it's a very important one, and it's the angle we are going to use to calculate the semi-variograms in specific directions. As you can see, we can make different directions for each pair of piezometers, as you can see here. For example, in this one, we can say the direction is 135. If you measure like this one, and here is the north, that one is going to be 135. For this one, for example, the angle is going to be close to 20 degrees. For this one, maybe around 30 degrees. And as you can see, there are different directions for the pair of points. and all these directions are going to measure with the azimuth angle. The azimuth angle is measuring from 0 to 180. In this case, for example, let's go to remove these things. Let's go to create a line here. In this case, we can say that the direction for this pair, it's from southwest to northeast. Other important thing is related with the number of combinations. For example, if we take these 2 points, these 2 piezometers here, 20 and 54, in this case, even we have 2 different combinations, we are consider this one as the same combination, because as we square the difference of these values, it doesn't matter if we put one term here or one term here, because as we square, we are going to have the same result. That's the reason, because we are going to consider this one as just one combination. Now let's go to see another combination to calculate the azimuth angle to clarify this idea a little bit more. Let's go to take a different point. As we are taking the azimuth angle here for this pair of points, for the piezometer 36 and piezometer 55, we are going to consider this angle here. This one is the azimuth angle. We are not going to take this angle here, because as I said, the azimuth angle goes from 0 to 180 as a maximum, and 0 and 180 is going to be the same angle because it's going to be aligned. Now let's go to see how many combinations we have for our pair of piezometers. As you can see, if we select all the points, you are going to see that we have a lot of combinations for all the pair of piezometers. We want to remove the selection, just click here. Let's go to select this area here, for example. You can see, but how many combinations? We can calculate that number using the next expression. This is the equation for the combinations, where we have 57 piezometers and we are taking from 2 by 2. Then this one is the factorial numbers, and then we can remove this one, and the total of combinations we can create is 1596 pair of piezometers, and this number is the number of points we can see here. Now it's time to see how we can process this information with Rstudio. Let's go to load all the information from 0. Then I'm going to remove all this information here. I'm going to take this one out, and I'm going to run all the libraries first. To load the data, I want to show you a different way to load the data, as we did at the video 2. Now we are going to import the data as an Excel file. I'm going to show you here. I have my Excel here. With the same columns. And I'm going to export that file. Then go here, from Excel, browse, open, and you can see that's the table we want. I'm going to select all this one, copy, cancel this one, and I'm going to paste here. I don't want this one because I have this one already here. Then I'm going to remove, and also I'm going to remove this one because I have this one here. and I go to run all this part all together. Then we have the both tables, 8 and 8 as a data frame. And now I'm going to run all this one together. Run. Okay, now let's get to see what things we have. We have the histogram, we have the density curve, we have the normal QQplot, the groundwater elevation with the bubble map, the Voronoi map, and the trend analysis for groundwater and the x-axis, and also the groundwater versus y-axis. And that's what we did at the videos 2 and 3. Also, we have a 3D interpretation of our data with a couple of graphs. This one and also this one. This one it's a good one because we can see a 3D interpretation of our data. Also here we have some information related with some statistics for our data over here. And also we did a test for the normality of our data. Now let's go to add the script to create the Semi-Variogram Cloud. Copy here. And as you can see here, we have a lot of things we have to talk about it. There are a lot of scripts. Let's go to start with the first one, this one. And in order to know what parameters we are using here, I'm going to show you how you can check the information related with this script here. Then just write a question mark, follow the variogram, run that one. You are going to get here at the help tab some information related with this script. As you can see here, you have an example. And you have here the definition of each of these things you can add to this script. As you can see, this one, for example, is the object and is defined here. The next one in our case is the location. No, sorry, is the data. Where is the data located? And the next one is the cutoff. The cutoff is how long you want to make your graph. In this case, I want 500 meters because the maximum distance is 453. Remember that we calculated that one with a specific script, and we have this one here, 453. We calculated with this script. It was this one here at the beginning for the some statistics. It was this one. Distance between the points. And that one is just to create the cloud of points, as you can see here. Cloud here. But if you want to add more things to your graphic, you can check this information and see what kind of things you can add. Now let's go to plot this one. Is this graph. Let's go to make this one bigger. And as you can see, this one is the same as this one. Let's go to close this one. Now let's go to view the information related with this object we created, that is the Semi-Variogram Cloud. Is this one here. When we add a view, that one is going to provide us a table over here. Run, and we have the table with the information. Then here we have the information for each pair of piezometers. Then we have the distance and we have the gamma value, the distance and the gamma for each of these points. As you can see here, we have 1596 points of information of our pair of piezometers, and that's the value we calculated here, 1596. Then let's go to run the next one to see what is the class of this object. And as you can see, the Variogram Cloud, it's a data frame. In the next script, we are going to export this table to a XLS file. If you want to know how this script works, just copy, paste here, question mark, then run, and you are going to have the help how it works. But just to have an idea, here we have what object we want to export, what information is the information from here, where we want to save that information, that's the link, what kind of format we want is this one, and also what kind of separator we are going to use is this one. Then just select all this one and run, and we are going to get the file. The file is going to save in the directory we indicated. It's going to be this one. In my case, it's going to be this one, and that's the file we created. Now we are going to work with this file to create the Semi-Variogram Cloud with Openoffice. Also, we are going to talk about this term here, the lag size. That is a very important parameter for the semi-variogram. And also we are going to create the semi-variogram omnidirectional. Let's go to open this one with Openoffice. And here we have to select this option here, comma, this is the table we want. Okay. Now I am going to remove, as you can see, this one is not the gamma, this one is the distance, and this one it's the gamma. For the other parameters, we don't have to be worried. Then I'm going to remove this one, and I'm going to remove all these ones, and I'm going to change the name of this one. Now I'm going to sort the data based on the distance. I want ascending. Then we have the points of information in ascending order. Then now I'm going to add a new column here, and I'm going to make a lags of 15 meters. It means that I'm going to take, for example, the first lag is going to be from 0 to 15. Then it's going to take these 4 points. I'm going to change the color, and here I'm going to indicate that that one is 4 points. For the next one is going to be from 15 to 30. That one is going to be the second lag until here, and I'm going to add a different color, and I'm going to do the same, and I'm going to do this one just for 4 lags to show you how it works. Now the next one is going to be from 30 to 45, and the lag number 4 is going to be from 45 to 60. As you can see, if we select all these ones and we make a graph, scaterplot, This graph is for the Semi-Variogram Cloud. This one is the same as this one. And also is the same the one we created with Rstudio. But the goal of this one is not to create the Semi-Variogram Cloud, is to create the lags and also the Semi-Variogram omnidirectional. Then I'm going to remove this one. I'm going to add here the title for this one. As we said, this data is for the Semi-Variogram Cloud. And now I'm going to add here the equation for the semivariance. And this equation is the one we was using to calculate the gamma. Now we are going to do the average for each lag, for the distance and also for the gamma. To do the average, just select this one, go here, that one is going to be the summation. Then select the parameters you want to do the summation, is going to be the distance. And then we are going to divide by 4 because it's 4 numbers. And we are going to do the same for the gamma. Then this one is going to be the lag one. And we're going to do the same for the next lag. In this case, we are going to divide by 42. Because 42 is the n, the number of page, right? And we're going to do the same for gamma. As you can see, we are taking all these values and we divided that one by 42. And that one is going to be lag 2. Now we are going to do the same for lag 3. In this case, we are going to divide by 76. Lag 3. And the last one is going to be lag 4. We are going to divide by 113. It's lag 4. Now we are going to create a graph where we are going to plot the cloud of points and also the average points. Then let's go to select from here. No, I'm going to select from here to this one. Just for the 4 lags. I'm going to edit this one a little bit. And now I'm going to plot the average points. I'm going to add here first the name for this one. So this one is going to be the Semivariogram omnidirectional. Okay, now I'm ready to add the average points. X for the distance. And Y for the average of the gamma. Now I'm going to edit these ones. And I'm going to change here the scale. I'm going to insert some labels. For the title is going to be Semivariogram. For X is going to be the distance. For in meters, Y is going to be the semivariance. And now I'm going to copy and paste this image to work on it. Okay, I copy and paste already here. I am going to add the lags every 15 meters. Now let's go to see what kind of information we can get from this graph, what it represents. We have 4 lags and each lag is 15 meters. We have also the Semi-Variogram Cloud for these 4 lags. Then in lag 1 we have 4 samples, in lag 2 we have 42 samples, in lag 3 we have 76 samples, in lag 4 we have 113 samples. As we saw here, lag 1 4 samples, lag 2 42, lag 3 76, and lag 4 113. The red dots are the average of the samples for each lag, and is known as a semi-variogram omnidirectional, and it's the experimental semi-variogram. This red dots has to be representative of all the lag 1, all the samples in lag 1. The same for lag 2, lag 3, and lag 4, and so on. Then when we decide what kind of lag size we want, we have to be aware that the red dot, the average, has to be representative of this section. If you think it's not going to be representative, then you can change the lag size for one more adequate to your data. It is very important that the experimental semi-variogram has a good lag size, because as I'm going to show you now, we are going to use, this one is the experimental semi-variogram, and this is the cloud of points, and we get the experimental semi-variogram doing the lags and then doing the average, and we get these points as we did here at this graph. And we want to make sure that the experimental semi-variogram is representative of our investigation area, because we are going to use the experimental semi-variogram to fit a mathematical model that is going to provide us continuous information. As you know, here we have information, but this information is discontinuous. We have points of information, but when we fit the mathematical model, we can say that we have the information in a continuous way for all the points, for all the distance. Then with this information we can create the interpolation map, and that's the reason because we need a representative information for the experimental variogram, and that one is going to depend on what kind of lag size you take to represent your data. Now let's see a few more scripts on Rstudio. The next graph we are going to create is going to be the cloud. Let me fix this one, but with a QGplot. Let's go to run all together. And that one, as you can see, it's a nice graph with the title, with the legend for the axis. Okay, and now let's go to see the next one. This script is to identify the pairs, as we did with ArcGIS. When we make the selection here, we can see on the map what is the pair of piezometers, right, for that point of information. Then we can do the same with Rstudio, and that's the script. Then in this case, we are going to use a distance of 500 meters. It means that distance over here, and it's going to be for the cloud, and we added this option just to have the possibility of digitalize the information. Then let's go to run this script. And now let's go to select one of these points, for example this one, with the left button of your mouse. Just make a square inside the point with 5 clicks. Then to finish, just press the button escape. As you can see, now it's selected. Then you have to run this one, and you are going to get what is the pair of points for the one you selected. We are not going to run the next script because this script is related with the Azimuth Angle and also with the Azimuth Tolerance, that we are going to talk about these terms at the next video. Then I'm going to remove this one at the moment, but we can run a little bit more scripts. Paste. Okay, I'm going to fix these ones first. Okay, now we are going to create the experimental semi-variogram, omnidirectional. Then we are going to create a G-stacked object, and we say that G is equal to all this one. The ID is the groundwater, it's our data. The formula, we are going to use this one, and the data is going to be from A. Then we are going to say that variogram 1 is equal to variogram G, this variogram. Then the variogram is going to appear here. You see variogram 1. Then let's go to see the first 6 values for this variogram. That's the number of points, that's the distance, and that's the gamma. Then let's go to see all the data. Now let's go to plot. That's the experimental semi-variogram for a distance of 150 meters. And as you can see here, let's go to move this one a little bit over here. Distance is 150 because R by default take maximum distance for 453 meters divided by 3. Then that's the default assumption for the software. If you don't specify what cutoff you want, the software in this case is going to take the maximum distance and is going to divide that distance by 3. And that's the reason because we have 150 here. Now we can increase that distance if we specify. Then we are going to create a variogram 1, but now with a different parameters. This one is going to be the cutoff distance, that is going to be that distance here. It means that we want 450 meters, and for the width we have 15 meters, and this one is the lag distance. Okay, let's go to run this one. And let's go to see now how the lag distance changes. As you can see here, now we have for the first lag, we have 4 samples. For the second lag, we have 42 samples. But if you compare with the other one, these values are different because we changed the cutoff and we add also the width. As you can see, these values for the 4 first, that's the one we created with the graph. Remember, it was 4 samples for the first lag, 42 samples for the second lag, 76 for the third lag, and 113 for the fourth lag, as we created here in this graph. Okay, that's the same values as here. 113 for the fourth lag, and also we have the same value for the average distance and also for the average gamma. 76 for the third one, 42 for the second one, and 4 for the first one. That's the same values we have here. Now let's go to plot this one, and it's this one. Okay, and also we can view the table for these values for all the lags. Now for the next script, we are going to see how we can create a graph with the pairs of piezometers. Going to plot this one, and this one is for each lag how many pairs of piezometers we have. Here is the number of piezometers, here is the number of pairs, and here is the lag distance. And here this continuous line is for the variance. Now let's go to plot the semi-variogram, experimental semi-variogram with the QGplot to make a nice graph. Let's go to main zoom, and as you can see here, we are going to talk at the next video, but this experimental semi-variogram doesn't have any seal, and we cannot interpolate with this kind of experimental semi-variogram. We have to remove that trend. We are going to talk about this term on the next video. Now with the next script, we can plot both graphs in the same page. Then let's go to, I have installed already this package. I'm going to run the library, and now I'm going to plot the graph. Now we have both graphs here. Then for the first lag is over here, we have this point. For the second lag we have this point. For the third lag we have this point here. For the third, this point, and so on. And this line is related with the variance, and we already calculated this variance at the video first. I'm going to show you the script. It was this script to calculate the variance, and the result is over here. Here is the script, and here is the variance for the parameter of groundwater, 2.19, and that's the value we have here. Sorry, let's open here. 2.19. That's all the scripts we are going to see today. And now we are going to see how to create a omnidirectional beam to see the lags on the map. We are going to use this graph here, and as you can see here, the beam direction for the omnidirectional semi-variogram has an azimuth of 0 degrees respect to the north. This red line is the beam direction. Now for the azimuth tolerance, that is going to be the angle from the big direction to this direction and also to this direction is going to be the 90 degrees. Then for our omnidirectional semi-variogram beam, we are going to have a shape like this one, where we have here the lag 1, lag 2, lag 3, and so on. The lags is going to be 15 meters, and also we have a term that it's called lag tolerance, that is the half of the lag distance. This one is the lag distance, the lag. But this term cannot be added on Rstudio, but in other softwares you can add the lag tolerance, but not in Rstudio. Now let's go to see how we can, let's go to remove these lines, how we can use this beam on the map. But first let me show you how it works on ArcMap. Okay, now we are in conditions to use these parameters. As you know, our lag size is 15 meters, and this distance over here is the one we call cutoff on Rstudio, and then it's going to be the multiplication of the lag size for the number of lags. Then if we have 30 lags and we make the multiplication 15 by 30, we are going to have 450. That's the distance. But if we add more lags, that distance is going to increase. Then for the show shared directions, we can select this option, and then we can change here the angle. Is this angle? No, it's the tolerance angle here. We can change this one. As we said, this angle is going to be 90, as I show at the graph here. It's 90. And the angle direction for the beam is this direction. You can move this one, but in our case it's going to be 0. And for the bandwidth, for the omnidirectional beam, doesn't make any sense. I'm going to talk about this term on the next video. Now, as you can see, the omnidirectional beam with a lag size and enough number of lags to cover all the extension is the same as the Semi-Variogram Cloud. Doesn't make any difference. If we take this one, we have the same as the Semi-Variogram Cloud. And if we add the angle for the beam and for the angle of tolerance, we have the same result. Okay, now let's go to see in a map. I have here a scale map with our location. As you can see here, we have the coordinates, and this is our piezometers. And I have here a omnidirectional beam that we can place on the piezometers. The distance from here to here is 15 meters, as we say. And here we have lag 1, lag 2, lag 3, and so on. Then let's go to place this beam on a piezometer. Let's go to start with this one, for example. And let's go to place at the center, approximately over there. And here we can say, for example, that piezometer 39 and piezometer 38, they are making a pair on lag 4. And also, for example, piezometer 39 with piezometer 34, they are making a pair on lag 4th also. And piezometer 39 with piezometer 37, they are making a pair on lag 7. As we said before, the lag 1 has 4 pairs, and I mark already these pairs on the map here to see how it works. Then let's go to see that ones. The first one is going to be piezometer 13. As you can see here, if we place at the center, piezometer 13 and piezometer 14, they are making a pair on lag 1. Also piezometer 12, here if we place, they are making piezometer 12 and 11. They are making a pair on lag 1. Also piezometer 7 with the 53 and piezometer 53 with piezometer 6. Okay, this is the end of this fourth video. Thank you very much for watching, and see you on the next one.